thank you for the introduction, Professor. And first of all, really big thank you to Professor Ludkovsky for organizing this and inviting me to speak. It means a lot to me because I've come from the department itself. So with that, let me just give a quick bio, who I am. As Ludkovsky said, I graduated from PSTAT about a decade ago now, which, wow, seems like it's gone pretty fast. Ever since then, I migrated north to the Bay Area, where I've worked in tech, like so many people do. I started as a data analyst at a small firm in the hospitality area that was acquired by Oracle. Subsequently, I moved to Stitch Fix, which is a retail fashion company that IPO'd in 2017. They do a lot of recommender algorithms, trying to match the best clothing for a consumer. And where I'm at now is Uber, which has a rides business and a food delivery business, which IPO'd in 2019. And currently I am working for the Uber Eats side of the house, in particular on promo optimization. So again, it's really nice to see here, especially with a lot of the students who might be interested in going further in schooling or breaking into tech data science. The talk today will be structured a bit to begin with around Uber Eats itself and the data science team structure. Perhaps that's interesting to some of you who might be, who don't really have the context. I'll spend the bulk of the presentation on technical aspects of promo optimization and some of the techniques we're currently applying. And lastly, I'll spend a few minutes before question and answer about my own observations breaking into tech data science. Oh, I think I have to start my video. Not sure. And
we can see you now. Perfect.
Okay, cool. On my orange background here. Okay. Yeah, so all of these are just my own observations, but I was thinking that it might be helpful as well to some of the folks who are wondering what to do. So let's give a quick what is Uber Eats and what is eater pricing. As you can see here, there's 3 pictures. This defines our marketplace. We have the eater in the top left corner, which is a person usually on a phone and usually on their couch, searching for food. They place an order. The restaurant receives that order. They will start beginning the preparation of that food. When the food is complete, we will dispatch a courier to go pick up that food at the restaurant, and then the courier will drive it back to the to the eater, and that transaction is now complete. As you can see, there's a mixture of the physical world and the digital world, and I think that's what makes Uber very exciting. And what happens is that it opens up tremendous complications about how do you run a marketplace efficiently. And so here I'm just kind of bombarding you with bullet points on what are certain decisions or actions we can take as market maker, as Uber, depending on the business goal. So, do we want to grow? Do we want to profit? What's going to be the action we want to take for any particular transaction? And we have all these levers that we can do. So, for example, if we just focus on the eater section, for any given eater who's looking at their app, we can decide: do we offer this person a promotion? How do we actually rank the restaurant feed? Do we know that they perhaps the probability of them placing the order will go up if we give them cuisine types that they like or places that they order from frequently? Say we want to boost the membership rates of our loyalty program. This is particularly important in a highly competitive market, like against DoorDash, for example. And so, so these are just a taste of some of the questions. And as you'll see that on each side of the 3 sides of the marketplace, there's unique problem spaces. In particular, like courier has a lot to deal with, like logistics and ETA prediction. And on the restaurant side, a lot is about kind of structural pricing with big enterprise chains and more like sales oriented stuff. So really exciting. And that structure of the marketplace leads us to how the data science team itself is structured. we basically try to service all the most critical areas of this marketplace. And what I've done here is put in kind of how I consider the silos. On the left, anything that has an outward-facing surface, so like apps, the Eater app and the driver app, they're separate. We definitely optimize that experience. The objective there being, for example, probability that someone completes an order or the time spent on the app itself. This next bucket is about onboarding more restaurants and interesting new verticals like actually placing advertisements in the feed. The third one, when you're running a marketplace, this is a live, real-time thing. This is not like we have to run a marketplace, and we have to make sure that that health is up. We have to make sure that we have enough couriers on the road at any given time to ensure that we can service the demand. So that's the real-time part of it. And then where I lie is this last silo on the right, which is pricing. And pricing is the go-to team to directly optimize economic outcomes, which would make sense, right? That's why it's called pricing. And that will be the focus of the rest of this presentation. In particular, Eater pricing. So optimizations around the Eater, the demand side, rather than optimizations around the supply side, which is courier pricing. Cool. So I also want to fix ideas a bit and like what are promos? I mean, I don't know if you guys have used the app or whatnot, but if we just look into Eater pricing, we have 3 distinct levers currently, and I like to think about them as short-term to long-term engagement. And what I've highlighted here, this weekly promo campaigns, is the team that I'm on. And what is meant by a weekly promotion campaign? Well, imagine you're the Eater. We've identified you as someone we want to give a promo to. You'll get a push notification like on your phone that looks like this left screen here. It's a little laggy because of all the GIFs here, but then if you open up the app, you'll see this pink billboard, which advertises the discount that you have on your account now. Then let's say you scroll into the restaurant feed and you're hungry and you choose whatever, this burger place, you'll see in your cart here that you're saving the promo. And we have this promotion manager tool, which allows you to choose if you have multiple promotions. And so that's what I mean by promotions. And when I'm talking about optimization, we're going to try to basically make this process optimal for a certain business goal. And we'll start to dig into that a bit more. Cool. So now that we kind of know the lay of the land here and what are promotions in this 3-sided marketplace, I want to scratch into the more technical aspects. So before we start with some equations or anything, I think it's important to step back and just this is a for-profit business, right? And so not just promotions, but any goal is going to be around some financial return on investment, right? So promo tech has 3 broad buckets. The first one I call user targeting, where through treatment effect modeling, we offer promos to users that respond most favorably to being given a promo. This is actually really nice in the world of promos versus the previous levers that I was talking about. Like if I want to change delivery fees or service fees, I have to apply that to every user at once. I can't differentiate, right? Whereas in the world of promotions, we can actually choose which users to give a promo. So there's this really rich kind of flexibility for targeting opportunities in the promotion space. The next bucket is the promo structures themselves. And so the promo structure, as you could imagine, is really diverse. It has a lot of parameters. The discount amount, do we want to have a minimum basket? What's going to be the total effective discount? How long is the duration of the promo? So you have all these parameters where just the base structure is actually quite important before you even get to any user targeting. And then the last one here is platform scalability. So this is a very, as you'll see, a lot of like my nods go to engineering, because this is a tech company at the end of the day, and we need a really good platform to be able to run some of the massive promotion campaigns that Uber Eats is responsible for. Like right now, my team, we're running weekly nationwide campaigns across 11 countries, hitting over 30 million users each week and responsible for over $15 million of spend each week. So we need a platform that can actually implement this at scale. And that means not just targeting users, but deploying emails and push notifications and a lot of the technical stack. So with these three buckets in mind, we all are rowing in the same direction, which is we want to minimize, for example, a key ROI metric, which is the cost per incremental billing. So a billing is, sorry if I didn't make that clear on the last slide, but a billing is, you can think of it as just whatever an eater spends on the platform, literally what we bill them. And when we run a promotion campaign, the whole goal is to get eaters to spend more to increase their billings. And if we offer a user a promotion and we don't offer another user a promotion, so like there's a treatment control, the incremental billings is that value of treatment billings per user versus the control billings per user. And we'll get into the cost part of it later, but we can start to just think of the promotion as trying to maximize incremental billings for now. So what we do actually in the user targeting space is rely on heterogeneous treatment effects. As the name implies here, the treatment effect, which in this case is giving or not giving a promotion, that affects individuals differently, right? People's backgrounds, people's price points, people's elasticities, people's engagement with the app, it all makes a big difference, right? So there's this super important function called the CATE, the conditional average treatment effect, which we'll be talking about a lot. But basically, when you decompose this function tau, which accepts user features in a kind of a traditional regression matrix X, is going to give us the difference of the expected value of Y. Y is going to be the business outcome, given that the user was in treatment, which is this T, minus the expectation of the billings if the user was in control, not given the promo, basically. So if we actually just make it a little clearer, we basically have users from 1 to n. We think of Y as this business outcome that we want to maximize, so call it billings. T is an indicator variable. For 1 is got a promo, 0 is no promo, and our covariates X can be things like what's the user's average basket size, days since last order, and their marketing email click rates. And like super high level view, what we do first is we run a randomized experiment so we basically flip a coin to assign T to our users, and that way we can learn the CATE function. And then once we have a CATE function that we use things like cross validations to assess what's going to be our best approach at the CATE function, then we will then rank our users from most incremental billings to least, if given the promo. And then last, we will develop this policy F, which in these slides here is a policy which maps any user feature set X to an outcome 0, 1, which is basically our decision whether in the next campaign we want to have this person be given the promo or not. And it all depends on their CATE score. So I know it's a lot. We'll move to an illustration here, but I'll just leave this on the screen for a sec. Cool. So let's actually walk through a very simple example. So imagine we have this data frame here, which has 5 users, and we've got it from running a randomized experiment. And when I mean randomized experiment, it's literally by saying, look, we'll take a promo and then we're going to give it to every other user. We're going to, scramble them, make sure that it's a purely randomized experiment. And that's why this column T has, 1, 0, 1, 0, 1, 0, whatever. Y, which is the billings placed in the promo period. So let's say we launch the promo on a Monday and we want to observe people's behaviors for, let's say, a week, because the promotion expires on Sunday. And then here we collect the outcome variable y, which is going to be, so this user 1 didn't actually place any orders in that period. User 2 placed $32.50 of orders, so on, right? And then let's say we also collected some of the user features before the experiment, right before the experiment began, and we have things like each user's average basket size and their click rate. So the next step then is to actually train the Kate function. Again, that's this tau. And note that, we are in expectations, and that's why it's called the conditional average treatment effect, because we can never observe the direct treatment effect, which would be considered like tau of I. So for any given user, if we wanted to just say, hey, what's their outcome, like what's their billings if given the promo minus their billings if not given the promo, and that's of course because in the training set we can only give a user treatment or control, but never both. So I think it's an important distinction as to why we adopt this conditional average treatment effect function. And then the last step is like assume that we have this Kate function. We will then run each user, plug in their X values, and then we basically can estimate what the tau would be. And then we rank them. In this case, since our objective is to maximize the incremental billings, we will rank, like the best user 1 is going to be the user with the highest tau. And so in this case, it's user 2. We expect if we gave user 2 a promotion, they would place $17.70 of additional billings on the platform versus if we did not give this user the promotion. And so we just repeat that for every user. And, like, for example, the worst user in this case is user 3 because the incremental billings this user would place is only $8.90 if given the promo. So it's better to, if we're going to say have a budget constraint and we can only give the promotion to the top 3 users, we're going to give it to user 1, 2, and 4 in this case. And so that's F. That's our actual targeting policy, which finishes this kind of approach we've taken. So in the next campaign, F, we've had this data frame prepared, and then we'll say, oh, okay, for this baby example, we're going to choose n equals to 3 users to get the next promo, and these are the users that are going to optimize the max incremental billings if given the promo. So that's who we would choose. Cool. Yeah, so that's an illustration of us actually like applying the Kate. Keep in mind, like we do this at a much bigger scale. Like, the data frame itself is 10 to 20 million users, and the number of features X1, X2 can go up to about 80 right now. And feature engineering is a massive part of the ability of the Kate to differentiate users, right? Or basically to have a rich and accurate Kate function. So in practice, this looks a lot gnarlier, but the principles are pretty basic here. So at this point, I think that like, okay, cool, like we know kind of the architecture, but how is the Kate function itself estimated? And there's a class of models called meta learners. And this guy Kunzel and his folks at Berkeley are the ones really pushing this literature forward. It's really nice because it builds on a lot of the kind of building blocks you learn in statistics and machine learning. And what's new about these meta learners is that basically you can combine sub models into kind of like almost a hierarchical approach to learn the Kate function. So let me just walk quickly through, like, so in this paper here, which I took a snapshot of, the notation, which I was using T in the past for whether the user got treated or not, that's actually W in this case. And then the 0 is users in control, and Y1 is going to be the outcome of users in treatment. So the T learner, this algorithm 1, is basically you're trying to estimate 2 functions, mu hat 0 and mu hat 1, which is a regression of all the users in control versus all the users in treatment. So it's as simple as that. Like you could literally partition your data into two separate models, and the model that learns the coefficients, so like M0 and M1, those can be simple linear regressions, or they can be, you know, multi-layer neural nets. There's this full flexibility, right? And then what you actually do in the last step is that the estimated conditional average treatment effect, the tau hat, is simply the difference of these two functions. And you can see that it's nothing too crazy here. The interesting part comes into like, how do you then assemble competing models? How do we use cross-validation to kind of, you know, test what's the best tau hat against, you know, we use cross-validation versus like ground truth data, we train, and then we do that multiple times. So that's algorithm 1, the T-learner, which is the simplest of the meta-learners. Algorithm 2 is this so-called S-learner, and they're called learners or oracle models because they're trying to learn about the treatment effect, right? So the S-learner is actually, in my mind, when I read it, I was like, well, this just seems kind of like a regression, because you literally are regressing Y on your feature set X, but you treat W, which is the indicator whether the user was in treatment or control, and you actually include this as a feature here, and then when you make a prediction in the tau function, you just, you know, you set it with 1 for this, with the same user set, minus setting the W to 0. So these things are these are just two of the most basic ones. There's like, you know, the X learner and so on, which get much more complicated quickly. But what I really like about actually these meta learners is that the base architecture is quite clear and quite simple, but the complexity and where you can really go to town is what model you want to plug in for M, right? Again, it's like linear regressions, tons of different trees, and then neural nets, and you can kind of play around, and then through cross-validation, you can actually compare which models are giving you the best performance, the sub-models, that is. But you can also then try different architectures like S-learner, T-learner, so on, and see if these different approaches yield different results. If you read the paper, there's like a lot of intuitions as to why, you know, for example, an S-learner might be better than a T-learner when, let's say, like your classes are very unbalanced. You have many more treatment users than control users, things like that. So this should just give you an intro about what is this mysterious Kate function, like how do we actually estimate it? And it's actually really just going into your data, trying out different models, and then using the important variable W to differentiate the treatment effect. Cool. So let me just see how I'm doing on time. Okay, sweet.
About 10 minutes, 10, 12 minutes.
Okay. So I just want to say that maximizing billings is not necessarily just the goal, right? Because every promotion has a cost involved. So actually, we need to think about a ratio, because what we're actually trying to do, like what I said in the past, was is this cost per incremental billing. And so if I were just to optimize for maximizing billings, I could be giving the promos to people that sure place a lot of orders if given the promo, but I would run up my promo cost. And so what I'm actually trying to do is identify those users that will place incremental billings, but also at a cheap cost, right? Because that's what this financial efficiency is about. So what we do actually in practice is not just optimize for the growth side, but we take the ratio so that it's the treatment effect of the cost upstairs divided by the treatment effect of the billings or the growth. And then once we solve this, we do the same procedure about ranking the users, selecting the best end users, and you know, this brings in a lot of complications because the denominator, when it tends to 0, blows up this ratio, and there's like this instability issues. So what we've done is we've actually moved away from point estimates for individual users, and then moved more towards like grouping users, so we get more, we don't need such granularity at the user base, but if we can define pockets of users and then actually give that whole pocket of user the promo or not, that's good enough, right? And it's actually it's actually more performant because we reduce the noisiness at the individual level. And so the last thing here I want to say is that because we've structured the problem this way, we can develop this so-called cost curve, which is on the x-axis we have the incremental cost, and on the y-axis the incremental value. If we give a promo, if we give a user a promo, then we can measure what's going to be the cost. So they spend money that Uber has to subsidize, but then they also bring in additional bookings, which is going to be, billings, which is the incremental value. And so you can think of this diagonal line, which has a fixed slope, as the Explore benchmark. So if I give the promotion randomly, I flip a coin, it doesn't matter how many users I give it to, I'm going to get the same return. There's always going to be a, for every cost, there's going to be the same value. There's like a linear relationship, right? But for a ranking model in blue here, if we can order the users from 1 on the left axis to all of them on the far right, then the intuition is that, let's say this dotted line here is the top 20% of users. And you can see that this segment U, for the same cost we would have spent on randomly giving out the promo, we get this additional value U, right? And this is this equivalence thing of saying I'm getting more efficient with my spend. So we develop these cost curves from ranking the users from best on the far left to worst. And notice how if your targeting model, of course, targets everyone, which is the top right point, then it will always devolve back to the randomized Explore, because you've given the promo now to without any kind of consideration of user features. So in essence, this is what we want to arrive at. And to finish it off, what happens is that we choose F, the targeting policy, to say, in this case, cut at the top 20% of users. And then we basically say, hey, all these users, give them a promo, and then all these users do not give them a promo. And then we're gonna maximize our objective function. Cool. So I think I want to just blow through this slide real quick. Basically, it's important that we run all our campaigns as A/B tests, which are the gold standard for drawing inference. Imagine this box is all the users that we want to give the promos to. The policy F defines some good users, which I call Z. Within Z, we still run it as a treatment versus control, where we randomly select users to get the promo and treatment, and versus those users in control. And in that way, we can actually answer questions about like significance tests, and then also do the correct calculation of incremental cost per incremental billing. So in other words, even after we've cut on the cost curve and we've kind of determined our qualified audience, we run an A/B test within that, where we randomly withhold the promo from some group of those users, those good users, because that's the way that we run the A/B test. Cool. So yeah, in a nutshell, hopefully, in summary, we run targeting models through treatment effect modeling, and then every promo campaign we run as an A/B test. And let me now then, because I want to spend a few minutes on this before opening it up to any questions. My own observations on transitioning into data science, and these are just my own observations. And it might be shared, I don't know, with other data scientists, what their opinions might be. But I thought for my own case, what I've learned, and also what's been really encouraging is to see events like this and the data science club and stuff like that growing at UCSB. I'm really happy to see that, because yeah, there's a massive opportunity and only in a more competitive and growing market. So with that in mind, some of my own observations for tech data science is that SQL frequently gets kind of a cold shoulder for some reason. People think you're just writing a query, but the sheer business impact that flows through queries is astonishing. If you get your query wrong, it could be extremely costly. And in my mind, as a practitioner, getting the query right and being good at querying, delivering queries at a high velocity, that's more important I would rather hire a data scientist, especially a beginning one, that over someone who has really good proficiency in Python or R. Like, don't get me wrong, Python and R are extremely important, but frequently in practice we're just making calls to libraries there, right? And unless you're going to go down the engineering track, you're not going to be constructing your own classes and building a repo, right? So a lot of, and this is not just at Uber. Like, I know Facebook, for example, like, their interview panel is extremely deep on SQL. And so things like Leet Code can help you here, because I know in like coming out of school, it's hard to have a database to like practice SQL on. Leet Code is actually really good for this. The second point there is more for like the stats and PStat people. Like, I think one of the things when I reflect on is that computer science and econ classes are really golden nuggets, which can help you differentiate yourself in a pipeline of data science candidates, right? I think, especially since I work on a marketplace, like I need to know about, supply and demand. I need to know about consumer behavior and elasticity curves. And these things, unless you take Econ 101, it's all going to be a little bit mysterious, right? Then this part here too, like in my own career, I think that one of the transitioning from UCSB to industry, I think one of the major lessons is trying to think about how you add value for a business, which is a for-profit entity, right? And one of the best advice I got was think about everything you're doing around the revenue line, which is if what you're working on is not generating revenue or saving on costs, your impact is possibly being diminished, right? And so these businesses work on money, right? And so you need to think about projects and teams that are close to this revenue line. I also think what's really important is knowing the kind of the objective function of your business leaders. So as a young data scientist coming into industry, you might think that, oh, running this, I don't know, this GLM and bootstrapping here that's going to be really cool. Like, I'm going to justify that, but it might not be exactly what even your DS leaders or like your business leaders value. Maybe they're just like, well, actually, a quick query dumped into a spreadsheet is what I need right now, and because that can be done in 30 minutes versus like 2 days, that's adding value. That's enabling me to make an action or a decision, which is going to further this business. So I think this has been one of the things that, I still struggle with, because come on, like, I love doing stats and stuff like that, but oftentimes you need to think about what is going to be the value of the deliverable, then open your toolbox, not the other way around. And then lastly, I think this is actually not even a joke. Like, either be an engineer yourself or have a close friend in engineering, because it just enables you to, especially in like smaller companies where it's hackier and like you gotta know all Linux and file systems. Like that's where you really want to lean on a good engineer. They're going to help you a lot because it is tech at the end of the day. So yeah. So with that, I think we have about 6 minutes or so for questions, and more than happy to answer anything you guys are curious about. And maybe before that, sorry, Prof, but I do want to say that we have opportunities at Eats, both for internships and full-time positions, and not just Uber Eats, but the whole umbrella of Uber companies. If you're interested or you just want to connect or talk, whatever, I'm more than happy to. Here's all my info. You can look me up on LinkedIn, and definitely open to more chats or trying to figure out summer internships or full-time positions. So with that, I just want to say again, big thank you to Professor Ludkowski for organizing it. It's really encouraging for me to see this kind of stuff happen. So it's been my pleasure.